Hello students, our next topic is stable nuclei. You go through this figure. This is a neutron-proton diagram for stable nucleides. So this is the line, this white line represents when neutron number is equal to proton number, but the stability nuclei fall in this line. This is the graph of neutron-proton diagram for stable nucleides. So we can see that up to this point, both these lines converge. They coincide each other. That is up to 20 or less than 20, we can find that neutron number and proton number are equal. Above which neutron number increases gradually. It is not at all equal to the proton number. So the important conclusions from this graph are: when light nuclei A less than 20 contains equal number of protons and neutrons, and heavier nuclei have greater proportion of neutrons. So nucleons we know that we have spin half and obeys exclusion principle. As a result, each nuclear energy level can contain 2 neutrons of opposite spin and 2 protons of opposite spin, similar to the energy level filling of atoms. So energy levels in nuclei are filled in sequence, just as the energy levels in atom are to achieve configurations of minimum energy and hence the maximum stability. So always this filling is always like this. That is one of the reason why light nuclei have equal number of protons and neutrons, and heavier nucleus has greater proportion of neutrons. You can see this is a simplified energy level diagram of some boron and carbon isotopes. The exclusion principle limits the occupancy of each level to 2 neutrons of opposite spin and 2 protons of opposite spin. We know that stable nuclei have minimum energy configuration. So first figure, boron 510. So the white is neutron and the red one is proton. Here it is filled, here too it is filled. So it is 5, 5, 1, 1 here. This is almost stable. Here we can see it is 11, 5, 11. Here neutron is filled level and one proton is not filled. Even then it is stable. You can see here it is 5, 12. So 7 neutrons are there. One of the neutron is above the level and there is a vacancy in the lower level. So this isotope of boron is unstable. So you can see carbon 612, it is fully filled, stable. Here too 613, this too is stable. Okay, this is how the protons and neutrons fill in each level. Obey exclusion principle. Next is, why is heavier atoms have number of neutrons greater than number of protons? What may be the reason for this value difference? So we know that protons are positively charged and they repel one another electrically. This repulsion becomes so great in nucleus with more than 10 protons, so that an excess of neutrons which produces only attractive forces is required for the stability. That is why the neutron number increases when the atomic number is increased. In the heavier atoms, proportion of neutron is more than proton. In any case, neutron number can be greater than Z, but it is never smaller. Okay, neutron number can be greater than Z, but it cannot be smaller than Z. Now, in nature, stable nucleides, 60% of the stable nucleides have even nuclei. That means there are n even number of protons and even number of neutrons, and 35% of them have odd even combinations, even odd or odd even combination. That means neutron number, if it is odd, the other is even, and vice versa. And only 5% of the nucleides in which there are odd number of protons and odd number of neutrons. This is the percentage of the stable nucleides. That means even number of Z and N are preferred mostly in nucleides. This is the inference we get from this separation. Okay, this also leads to one more conclusion, that there are energy levels, nuclear energy levels present. So there is a filling of nuclear energy levels similar to the electron filling. Now nuclear decay. We know that nuclear forces are limited in range. It has a very short range force. As a result, nucleons interact strongly only with their nearest neighbors. So this effect is referred to as saturation of nuclear forces. So because of this Coulomb repulsion of protons is appreciable throughout the entire nucleus, there is a limit to the ability of neutrons to prevent the disruption of a large nucleus. This limit is represented by the bismuth. Bismuth 83209. This is the heaviest stable nuclei, above which the nuclear force has no range. That is, all nuclei with Z greater than 89 and A greater than 209. They spontaneously transform themselves into lighter ones. Spontaneous transformation occurs and they become lighter nucleus through the emission of one or more alpha particles, which can be, which is a helium nuclei. This is the alpha decay, or it can be by beta decay, positron emission, or by electron capture. This disruption or the spontaneous transformation can take place. So these decay, alpha decay, beta decay, etc. will be dealt in detail in the next chapter.